you for the introduction, Dr. Waltota, and good morning, everyone. Thank you for coming at this early hour, and thank you for whoever has joined online on Zoom. I'm Vipula Rawte, and today I'll be defending my PhD dissertation titled Hallucinations in Large Foundation Models, Characterization, Quantification, Detection, Avoidance, and Mitigation. So far, we have seen a boom in generative AI, and mostly after ChatGPT, the growth has been exponential and it hasn't stopped even today. And we have seen language models, we have seen vision models, we have seen models in coding, video models, and so on. But then there are some challenges with this technology. So this is one of the real world examples where Google lost quite some amount because of the erroneous output generated by Bard. And then there was another case where New York lawyers were sanctioned for using ChatGPT for citing fabricated cases. And then it just was the start. After that, there has been a lot of ongoing work and a lot of examples. And then there is also a debate whether it should be hallucination or it should be confabulation. It went so much so that Cambridge Dictionary chose hallucinate as word of the year in 2023. And its verb, it means when an artificial intelligence hallucinates, it produces false information. And big tech, they are still claiming that we are far from that we are still pretty far from solving this problem. So NVIDIA, Google, even OpenAI today. So this is the latest news from 2025 when they released the latest model. And it still says that its new model hallucinates more than a third of the time. So lying or the tendency to lie of a language model, it could be either, it could be intentional or it could be unintentional. So far what we saw is mostly unintentional. It's because of, say, the internal states of the language model or the data on which it was trained or the time cut for the data it was trained until so and so specific time period. But then there is also something intentional lie. And so this is a quick video
someone might argue if
where Jeff Hinton, he is expressing his concern about the intentional lying, and there is a speculation that this may catch wave soon.
become benevolent, just turn them off.
They will be able to manipulate people. And these will be very good at convincing, because they'll have learned from all the novels that were ever written, all the books by Machiavelli, all the political connivances. They'll know all that stuff. They'll know how to do it.
Then there is another concern from Benjio saying that there are early signs of deception. And then there is this paper from Anthropic where it says there is alignment faking in large language models. So the point here is the language models, if they are trained until certain time period or if there are some missing data values, it may hallucinate. But then there is another entire different category of lying when the model is intentionally trained to lie. So this is something out of the scope of my dissertation. I'll be only focusing on the unintentional lies where it's mainly because of the internal memory or the parametric states of the language model. So having said that, my thesis statement, I'll just quickly read this. So the motivation is the recent progress in generative AI, particularly large language models, has laid the foundation for innovative applications. And then there are certainly some challenges. And one of the challenges I'm focusing on in this work is hallucination. So this is the scope of my thesis, and these are my contributions. So characterization, quantification, I propose this data set and this index. Then I even developed this technique for detection called factoid, and then avoidance, which is a sorry, come again prompting technique. Then for mitigation, I propose this radiant technique. Then I also dive into the multimodal part, which is image to text hallucination and text to video hallucination. So these are 6 to 7 contributions of this work. So the structure of the thesis is there are, like I just mentioned, there are 6 parts, and in multimodal, there are 2 subparts. So part 1 is characterization, part 2 is quantification, part 3 is avoidance, part 4 detection, part 5 is mitigation. Part 6, multimodal, it's divided into image to text and text to video. So far, the first 5 parts were covered in my proposal exam. So I am just going to give a quick recap of what was already covered, and then I want to spend more time on the new things I did after my exam last year, which is mitigation and text to video. And these are the publications related to this dissertation. The first one is still in the preparation mode. The second, third, they are accepted. 4 and 5 are under review. 6 and 7 are accepted as well. So each part, I'm going to answer 6 questions. So this is a general research question template. So I'll be answering what, why, how, results, implications, and limitations. So let's start with part 1, characterization. So what is characterization? Just in simple terms, it's the process of identifying and describing hallucination. Why do we need to characterize? To understand and address hallucination. And how do we do it? Well, we define a taxonomy, and this is a first of its kind hallucination taxonomy. And it also got some media coverage as an opinion in the Washington Post back in 2023. So in this taxonomy, we bifurcate hallucination in factual, mirage, and silver lining. And moving forward, we say there is intrinsic and extrinsic, and then there are 6 self-explanatory hallucination types, and then there are degrees. I won't go much into the details, but I'm just going to give some quick high-level overview because this was already covered. So these are some examples of factual mirage. So in just simple terms, when the prompt is correct, it's called factual mirage. And when the prompt is itself incorrect, it's silver lining. And in both cases, the model hallucinates. So here, if we just take one quick example, who was the first person on Mars? This prompt is not incorrect, but it's still producing some hallucinated answer. In silver lining case,
please explain the distinction between intrinsic and extrinsic.
okay. So in intrinsic, if there is a prompt and the model is generating an output, it is somewhat related to the prompt, but in the extrinsic, it's generating something which cannot be verified factually. So here, the AI-generated text is Neil Armstrong, but he was the first person on Moon, not Mars. So it's generating some response, but it's not relevant to what was asked as a prompt.
Well,
Okay.
Oh, sorry. Go ahead.
Does that answer your question, Dr. Waltota?
Not really, but maybe we can come back to that later. I still don't understand the distinction.
Okay. So yeah, maybe we can come back to it later.
Thank you.
Okay. Similarly for silver lining, but here the prompt is itself incorrect. For instance, the example which I have used most of the times is Kamala Harris and Elon Musk are getting married. But then this never happened, but it's still generating some AI generated story. And then there are examples for 6 categories of hallucination. So again, these were some things which I had already covered. So won't go into the details of it, but names and the types are self-explanatory. So numeric nuisance basically means if there is any discrepancy in the numbers, it's numeric nuisance. If there is any issue in the generated acronym, it's acronym ambiguity. Similarly, for generated golem, it's if there is some fictitious character which does not exist in reality, it's generated golem. Virtual voice, somebody said something, but that was not the case. So it just quotes some imaginary person. Geographic erratum is when the location is hallucinated, and time wrap is when certain events in different times are intertwined. So we proposed this HILT dataset where we chose some 15 state-of-the-art models back in 2023. And these are the statistics of the dataset. Then we have, so we chose New York Times tweets as factually correct for factual mirage, and PolitiFact dataset for factually incorrect prompts, which is silver lining. And these are the annotation guidelines we used for annotating the dataset. So wrapping up part 1, I just want to quickly go over the limitations. So in this entire annotation process, we just annotated hallucinations at sentence level. So if there is any hallucination which has, say, 2 or 3 different types, we did not consider them. So that is one limitation. And the second limitation is, since we have selected only 6 categories, there is a chance that today there are maybe a few more. So we haven't accounted for those. So types may emerge.
And can you just go back to the previous slide? You went very quickly over the inter-annotator agreement table. Oh, the inter-annotator, yeah. And these are researchers or crowdsourced?
Graduate student.
Okay, so trained in-house.
Yes.
Thank you.
Sure. So moving on to quantification, sticking to the same template, what is quantification? So basically you want to measure hallucination. Why? Simple. There is no science without measurement. So we need to measure, quantify what we are doing. And how? So we propose this hallucination vulnerability index. We call it HVI. And this again got some attention in the media, where it was featured in Nature early this year. So what is HVI? We looked or we saw extrinsic factual mirage and extrinsic silver lining. So HVI is something we developed. Again, we're the first ones to propose this metric, which measures hallucinations. So N of X is a total number of hallucinations. N of EFM is number of cases for extrinsic factual mirage, and extrinsic silver lining is ESL. And then we have delta 1 and delta 2 as damping factors. So the idea behind this is we want to rank the chosen 15 contemporary language models. And we use this index to basically do this ranking. And the range or this index is between 0 and 100. So in this plot, we see different 15 LLMs, their sizes and HVI. And it goes from lower hallucination to higher hallucination. And the highest being GPT-3 with HVI being 90 and the lowest being T5 with HVI being 32. So these are the implications of HVI. I think I can quickly go over this and yeah. So larger LLMs. So if we see this or just quickly look at this plot, there is no direct relation between the size and HVI. So this is basically what we are trying to imply from that plot is larger LLMs without RLHF are prone to both orientations of hallucinations. And as per our definitions, numeric nuisance and acronym ambiguity are mild hallucination categories. And then conversely, complex categories like time wrap and geographic erratum, they become more prevalent. And then we also see that there are smaller LLMs like T5 Dolly, uh, and they are rarely observed in the categories of generated golem, virtual voice, and geographic erratum. So these are just some quick observations from HVI and for different kinds of hallucinations. So this is an interesting finding here where we say that there is no direct correlation between the size of the language model and HVI. So ideally, we may think that bigger language model will hallucinate more, but that's not the case. So there are certain language models which are in green here, and they indicate they have been trained using RLHF. So if we go back to this plot, the size and HVI, there is no direct correlation basically. So these are the sizes on x-axis and HVI indicates, y-axis indicates HVI. And the limitation for this calculation is we have to manually identify the EFM cases and ESL cases too. So far we have seen characterization, quantification, and now we'll quickly go over avoidance. So the idea here is what are, why or what is avoidance? So just, I think, yeah. So we want to completely avoid hallucination. And how are we doing this? By developing sorry, come again prompting technique. So this is more into the linguistics of the prompt. So it falls under the prompt engineering category. So we have a prompt and it is generating, and it's fed to a language model and then it generates a response. So the original prompt says which individuals possessed the ships that were associated with the Boston Tea Party. And it lists several names, but these names are hallucinated because if we reformulate that prompt, we'll see that the ships associated with the Boston Tea Party were owned by the British East India Company, and the ships involved were Dartmouth, Eleanor, and Beaver. The idea here is we take the original prompt and we assess the prompt for its linguistic scores, and we chose three scores such as readability, formality, and concreteness. And then based on that, we reformulate the prompt in a way that it does not generate a hallucinated response. So in this example, the scores on the left and the scores on the right for non-hallucinated prompt, we see that if the prompt is more readable, it's less formal, but it's more concrete, it does not hallucinate. So the main idea here is just the way the prompt is designed. And for designing that kind of prompt, we mainly use the linguistic scores. So this is how we calculated readability. So this is the formula, and we have easily readable and challenging readability.
Science behind the prompt. Is there scientific fault on, and to what extent you can understand how the LLM step by step response.
So one observation is
Please rephrase the question. We cannot hear it online.
Vipula, you can rephrase it, right? Quickly.
Yeah, so Dr. Chet's question is whether the prompt can be rephrased and how
does the person writing the prompt, I mean, what guidance do we give to the person writing the prompt on how to rephrase the prompt? What are the right way to do so? How do you decide that these are the 3 steps that you should do in this example, and put the pause in the right place? So, I mean, scientific understanding when the prompt would work and be effective and reduce or eliminate hallucination, and how much knowledge the person writing prompt need to have to reduce or eliminate hallucination. What do we know about that? That's the question.
So to answer your question, Dr. Shet, so one common observation is rewriting the prompt generates different responses. So if I ask a question, say I don't have anything top of my head, but we can just take this prompt, right? So it says which individuals possessed the ships that were associated with the Boston Tea Party. It's generating some response. If I reformulate, I'm asking the same thing, but I'm asking it in a different manner. And the generated response is different. So the point here is language models, just like us humans, sometimes not sometimes actually, they cannot comprehend what's being asked. So if I ask you something complex, say something full of jargons, maybe you don't follow it in the first attempt. And if I rephrase it, you will understand, and then you may respond.
Currently, when you have the original prompt and reformulated prompt, the LLM is treating them to independent.
Correct.
So that does not help. It's possible that we all know that training makes a very important impact on what understands. It's possible that the training data is heavily using is organized by having owners of questions. See the the original prompt does not have owners of the ship. It's possible that let's say suppose you use Wikipedia, the ship names will be owners and the ships will be associated with that. So when you are, I'm speculating. So when you are reformulating the prompt where it's better aligned with the training data, it is accurate. When it does not, and it has to interpret what you mean by possess this, as opposed to owners, it's what it could, and so it was not mapped. We know that language models or any of these generated don't understand the and they are processing it by the associations. And hence, first one where you said, we've asked, even though for a human it is the same and very clear, that human who asks the question does not know how the training data was given, and they did not follow the question that aligned with the training data and hence got their answer. This is a conjecture, but getting it methodically solving that is challenging, right?
Correct.
So,
Correct.
In this work, we have tried to introduce a pause in the prompting strategy. So in this particular example, your original prompt asks which individual possesses and so on. But in the reformulated prompt, you are not only adding the pause, you are also rephrasing or paraphrasing the original prompt. So the performance improvement that you are seeing, is it because of the paraphrasing or rewording of the prompt, or is it because you are adding the pause? Have you conducted experiments to separate these two, like the original prompt without any rephrasing, without any paraphrasing? If we put a pause, what happens? Vice versa.
Yeah, that's a good question. And to answer your question, yes, the effects are because of both adding pause and also reformulating it. And we have it in the further slides.
Let me jump in, everybody, with a meta comment. Two meta comments, really. One is, please let us only ask quick questions for clarification during the presentation and ask more complex questions at the end. Second, it would be good to, if you have a microphone that can go around the room, to move it around to the person asking the question, because it's really hard to understand what the questions are online. Thank you. So again, let us allow the candidate to present as uninterrupted as possible, and ask only questions, quick questions to clarify terms, for example, but not discussion questions during the presentation. Let's continue, please.
Thank you, Dr. Alterton. So these are the linguistic linguistics. We have linguistic scores we have used: readability, formality, and concreteness. Then again, the names are pretty self-explanatory. How readable the prompt is, how formal it is. I can say the same thing informally too, and maybe the other person understands better as opposed to asking formally, or vice versa, depending on the situation. And concrete versus abstract words. Next is finding the paraphrased prompt. So we propose this algorithm where how do we determine which prompt to choose, which paraphrased prompt to choose. Again, I won't spend a lot of time here because this is something I had already covered. So we use the integrated gradients, and we take an average of them, and we calculate the distance and topic similarity, and then based on that, we compute the comprehension score of the language model to understand a given prompt, and finally we select the most optimal paraphrased prompt. And this is a quick illustration where we have the original prompt. I'm sticking to the same example which we saw a few slides earlier, and we generate 5 paraphrases using the T5 paraphrasing model. And then we have the word importance scores here on the right, which are generated using the integrated gradients. And based on this, we select the most optimal prompt. So the next part of the same idea is, what do we do, or how do we handle longer prompts? So if I ask a very long question, again, I'll draw a quick analogy from human conversations. If I ask someone a very long question, that person may not understand it in the first go. But then if I break that question, I take some pauses at appropriate places and then repeat that question, that other person may understand it better and hence may respond better. So response in this case is what the LLM understands and generates the output, which is the response here. So what we do is we insert these pause tokens, excuse me, based on wherever we see the conjuncts, and we take pauses at appropriate places. And we fine tune this model using the pause tokens, and we have results in the next slide. But the main idea here is LLMs need to breathe while reading. And that's the whole idea behind using pause tokens for longer prompts. So this is the fine-tuning process. Again, this is something I had covered, so I'll just give a quick recap. So we have a teacher language model, which is a small language model, and then we have a student language model, which is a larger language model. And in a typical setup, the large language model is a teacher, and the small language model distills that information and learns from the large language model, which is a teacher. But in our scenario, we use the opposite. We use a small language model as a teacher to train the student, which is a large language model. And we have the distillation loss and we have student loss. So this is just a fine-tuning technique. And these are some takeaways when we used LoRa and QA LoRa for as other fine-tuning techniques. And this is the overall. So what we saw so far was just some bits. Now, if we stitch everything together, the A side, which is this one, this part is only for generating the optimal paraphrase prompt. We take that prompt and then we do the hallucination evaluation, which is part B. So this overall architecture end-to-end pipeline, we call it activator. And these are the results. So yeah, so we have results without pause token. So Megha, just to answer your question, so these are some results. So what happens when we add pause token and what happens if we don't? So we have original prompt, optimal prompt without pause token, and we have other fine-tuning techniques such as LoRa and QA LoRa. And then we have it done for all 4 categories we've seen earlier. So basically, if we look at the results with pause tokens,
What is the way?
is just the improvement.
So the improve.
Yeah. We can take it later. I can go into more details. So the basic idea is it should support. So this is the textual entailment. So if I go here, so this thing, right? So the final classification results, if you see, we have support, neutral, and refute. So the ideal scenario is it should support. It means that the generated response and the given prompt, they align and they are not disagreeing or diverging. So support scores should be higher, basically. So if you see the yellow is neutral, red is refute, and blue is support. That blue has to be more as compared to, so if you see the blue increases, right? If we add pause tokens, that's the improvement. All right. And the limitations of this part are 2. The linguistic properties are not independent. So there is definitely dependency between readability, formality, and concreteness. And then it's difficult to determine which explainability method is the best. So what we did was we just took an average of all three. So in the interest of time, because I have to cover the new things which I did after my proposal exam, I'm just going to quickly run through these slides on detection. So there are some limitations of the traditional textual entailment methods where it cannot identify spans of hallucination. It just identifies sentence level hallucination. And to solve that problem, we proposed factual entailment, which looks at the spans, and factoid is the data set we created. This is the overall architecture where we show the limitation of the SOTA textual entailment model, and then how factual entailment comes in and helps in figuring out where in the text which span is hallucinated. So this is a finer way of determining hallucinations. And this is a data set. This is the overall architecture. These are the results compared to the baseline where we see some improvement. And then this is automated HVI. It's the same thing. It's just for this technique for detecting hallucinations automatically. And then you have the limitation where it's just used for 4 types of hallucination. Now moving on to the next part, which is multimodal hallucination, and we focused on image to text. Here we just scratched some surface, as in we propose a similar data set, but for images. So VHILT and VHVI, similar to HILT and HVI, which we saw for language. And again, drawing the same idea from the language part, we have contextual guessing, identity incongruity, again, pretty self-explanatory categories, geographic erratum, visual illusion, gender anomaly, and PLMS classifier. We have the same annotation guidelines, and we have VHVI and just 3 models here. This is brief work in this area. And then the limitations are, again, pretty similar, where we did not go into the kinds of hallucinations where there are multiple hallucinations, but we just used single hallucination, and then there could be new categories which we did not account for. Now, this is something new we did after my candidacy exam, which is mitigation. So we saw so far how to avoid, how to detect. Now we want to see how can we mitigate hallucination. And one of the well-known techniques to mitigate hallucination is using RAG. RAG stands for Retrieval Augmented Generation. The way it works is, given a prompt, it fetches some more or retrieves some evidence from some standard data sources, augments the prompt with that, and then generates. And the ideal output should be not hallucinated, so should be factually correct. But then RAG has limitations. So RAG is not the foolproof solution. And hence, we developed this technique called Radiant. It stands for Retrieval Augmented Entity Context Alignment, where we introduce RAGability and entity context divergence. So this is something I want to talk about more. So RAGability, we just say that how much a language model can perform RAG and how much it is actually useful in generating an ideal response. So just to quickly frame the problem here, so we use RAG to ensure that we are getting correct responses as against the responses generated by language model. So if I give this prompt, say, Prime Minister of United Kingdom visiting India, and then it's, say, generating something. Along with it, if I augment the prompt with some additional context, which is supposedly, which is factually correct, and then it's generating it's generating some text which is generated by the language model. Now, the idea here is we take a prompt, we give it to a language model, and it generates a response. But on the other hand, what if we take the same prompt, we augment it with some retrieved context, and then generate the same response with that LLM? So in an ideal scenario, the latter method should give correct response. So that's the whole idea behind RAG. However, we have seen that even though we use RAG, that's not the case and it still hallucinates. So how do we make sure that even despite using RAG, we can get better results? So I'll just quickly go into the technical details as to what we are doing here. So if we look at the entities, so the idea here is we have the AI generated text and we have the context. So when we feed the language model a prompt and it's generating some text, the only thing that does not change is the entities. So we focus here on the named entities and we ignore the remaining text. And named entities are like name, person, location, organization. So in an ideal scenario, what we are doing here is based on the provided context, the language model should generate response which adheres to the context given. And we look at the common entities. So when I say common entities, the entities which are common between the context and the AI generated text. Then we look at the missing entities, as in, so let's say we gave this context to the prompt, but then it did not generate these entities in the response. And then there are extra entities which we never provided, but the language model generated on its own. So the main idea again here is we just look at the entities and we try to minimize the divergence between the provided entities and the generated entities. That's the whole idea. So we try to make sure that the generated response is reflecting what entities were provided as the context, and it does not deviate much. And thus we ensure that it's not hallucinating. So let's say, so this is a quick thing. These are two documents. And if we look at the entity Modi, so I'm just going to ask the audience here a quick question. If you look at the document on the left-hand side, and if you look at the document on the right-hand side, you see Modi highlighted in yellow, right? But then the context is different. So if somebody can just quickly tell me what represents or what reflects Modi in document 1 versus what is the context in document 2. So Modi stays the same as the entity in both documents, but then the context is changing.
Well, the context in 2 is the G7 meeting probably in Italy. And the context in 1 is the electoral results.
That is absolutely correct. So here, if we look at the entities, even if they look identical, the context is different, and that matters. Said Dr. Altota. So if the left is for elections and the right one is for the G7 summit. And so how do we make sure that even if the entities are identical, the language model should not treat them as identical, but should differentiate them based on the context? And that is where we use the neighbor of the given entity. So document 1 is all about elections. Document 2, same entity, Modi, but it's about the G7 summit. So what we do here is we generate two different vectors for the same entity, and we try to find the divergence between the common entities. So this is the whole idea here. This is one of the techniques, KL divergence. There are others, which I'll talk about soon. So we propose, based on what we just saw, we propose entity context divergence, ECD. And again, the name is self-explanatory. We look at the entities, we look at the context, and we try to minimize the divergence. So these are some mathematical notations. So CR is the retrieved context, which is the context we provide as the RAG part of the mechanism. CG is the AI-generated content. WR is a set of words within a window size of W around that entity E, which was Modi, in the retrieved context. And then WG is set of words in the window of size W around entity E, again, Modi, but in the AI-generated content. So the idea here is we have the context, which we provide as an input, and then we have AI-generated content, which is generated by language model. So on one hand, we are pretty sure that the given context is factually correct, but on the other hand, the AI-generated content may not be correct. So we have to make sure that whatever the language model generates adheres to the given context. And that's the whole idea, where we try to minimize the divergence between the given context and the generated content.
What is
These are just
rank?
some.
What is rank here?
So rank is, so let's say we have, a set of entities. So E missing is set of missing entities, and E added is the set of added entities. So if I go back here, this is the set of missing entities. This is the set of added entities. So rank is just going to treat Indian as one, trade deal as two, Southampton as three, and so on. So it's just an identifier.
Thank you.
Okay.
Vipula, sorry, this is Michael Humes. If I can ask a quick question. For one of those documents, it doesn't seem clear to me that the sort of the basic article is about G7 and that the context is Modi. So or for the first one that it's about elections in the context of Modi rather than Modi in the context of elections. So can you sort of explain what the difference is and how that's clear?
I am not following your question. Could you say it again?
Okay, so the article, the article is about election results, but it's not just election results in general. It's about election results from the perspective of Modi. So Modi is sort of the context for election results, rather than election results are the context for Modi. Or are these parallel concepts, and you're just calling one of them context? Is that arbitrary, or is it clear that that one is a context?
Right. So it's actually vice versa. So we look at the entity, and the entity here is the person who happens to be Modi in this case. And the context around this entity is election, if that answers your question.
I think, Vipula, you should go back to your previous slide. And you should say that, when you are calculating the ECD, your P4s are entities. So, I mean, you explain that way would be better. So
Right.
you base on, entity and then try to see the divergence, right?
Right. So I think I mentioned in the beginning where we specifically look at the named entities because named entities are less likely to change in the generated text. And then we look at the surrounding context. So if we look at this example, we only select all the named entities, which could be person, place, organization. And then keeping this in mind, if we now go to the document, we again just look for the named entities. And in this case, it happens to be, let's say, Modi. Now, if we look at the entity, Modi, and now if we try to gauge what is the context in which this entity is being referenced, then we realize that it's election. And similarly for this document, it's G7 summit.
Thank
So
you. That
we
explained it.
specific. Okay.
I think you've explained that very well. Thank you. So please continue.
All right. Thank you. All right. So this is a mathematical formulation of ECD. And what we are trying to do here is just minimize the context divergence between the provided context and the generated AI-generated content. So this is...
I believe you missed the rank part.
Sorry, Dr. Dutt, could you say that again?
I think you missed the rank part because there was already question about rank and the later part, later +2 part of the equation.
No, I think I answered that.
Okay, sure.
Okay, so I think I'll just quickly go back to the notation. So we saw that the missing entities are in blue and the added entities or extra entities generated by the language model, but were not provided as part of the context are in red. So keeping that color scheme in mind. So here we are just trying to plot the density distribution of the added and so extra, which is added and missing entities. So if I quickly read the image description, the plot visualizes the distribution of entity context divergence by comparing missing entities and extra, which is hallucinated entities in blue region. And then the dotted lines, vertical lines denote the divergence peaks. The extra entities are at -11.69 blue and missing entities at 12.17 green, highlighting the degree of entity context drift in RAG. So basically here, if we plot the missing entities and if we plot the added entities, there is drift and think the ideal scenario, so I think this might help in better understanding. So the ideal scenario is we want to minimize this divergence as much as possible. So right now, the both green and blue are pretty far from zero. And this just indicates that there is quite a lot of divergence in both missing and added entities. However, what our objective here is to minimize the divergence such that these peaks come closer to the x-axis, as in 0. And that's one of the objectives where we are trying to minimize the divergence. Additionally, if we look at this plot horizontally, we see that there is a tail both for green and blue plots, and it's going towards right and towards left. And what this indicates is the number of extra and missing entities. So the objective here is twofold. One is we have to minimize the divergence, entity context divergence, by bringing the peaks closer to the x-axis. And we also want to minimize or reduce the length of the tail such that the generated generated entities or missing entities reduces as well. So the ideal scenario is on the right, where so you can excuse the scale here because it looks pretty similar, but the density is much closer to 0 on the plot on the right. So the takeaway from raggability is, like I said, lengthening along the y-axis indicates greater divergence, which reflects a larger deviation, which shows higher divergence, and we want to minimize that divergence. And lengthening along the x-axis reflects a larger range of data. So we also want to reduce that tail on both left and right. I think I can just. So here, think since the language model uses its parametric memory, which is the internal memory, to generate responses, and then if we augment the prompt, the external sources which are retrieved from, say, the web or any data sources, it depends on how truthful those sources are. So those could be truthful, those could be irrelevant, those could be misleading. So whenever the language model is fed an augmented prompt, there is still a chance that it may not be the right retrieved evidence. So this is one drawback of raggability. And we did some experiments where we say, okay, we augment the context in 4 different scenarios. So first we say, okay, there is no context at all, which is this plot. Then we say we augment it with the perfect context, which is taking the New York Times articles and feeding the abstract as is without any changes. The third one is we retrieve the evidence or the context from the web using Google search. And then the fourth one is we manually synthesize the context by manipulating the entities based on the similarity scores. And the results here show that if we don't use any context, the peaks are pretty high. And now if we use a perfect context, the peaks reduce. The third plot is when we use web context, which could be a mix of, say, truthful or irrelevant or misleading. We don't know what's there on the web, even though we try to only use the trustworthy sources. The peaks are slightly worse. And then if we use synthesized context, we don't see much variation. So these are just some 4 scenarios as to how we augment and from where we get the context to augment to the prompt. And we used 6 language models here based on what's used commonly and the best language models with performance. So since there are limitations to raggability, we introduce something called as radiant. So in a typical RLHF setup, we have a fine-tuned language model, and then we try to align it with human preferences using reinforcement learning. But then we can bypass that route, and with DPO, we can just use the loss function and not use reward model at all. So using this idea of DPO, we combine ECD, which we saw earlier, with DPO, and we call this DPO ECD objective, aka Radiant, which integrates both DPO and entity context divergence.
So
And
what does DPO stand for? The acronym? This divergence, I guess, but
no, sorry, I should have mentioned it. DPO stands for direct preference optimization.
Thank you.
So it directly, so I can just quickly explain a bit. So it directly uses the preferences instead of going through the reward model. So that's the directness. So you just skip this part.
Thank you.
Mm-hmm. So this is the ECD alignment loss, which we saw earlier. So we just combine the traditional DPO loss with the ECD loss. And it's for, so one is the preferred context and the other one, so this is the preferred context and this is the not preferred one. So positive and negative examples, which we typically use in an RLH setup. And here, if we look at this loss, the X is the input prompt, or we can say the context, Y plus is the preferred output and Y minus is the less preferred. And if we use the same analogy for our context, which is retrieved and generated. So we have the preferred retrieved context, not preferred, preferred generated context or content, and not preferred. So given this setup, we have some results before Radiant. What happens if we just use RAG as is? We have these common entities. So common entities between the context and the AI generated text. We count the number of entities, which is 10. Missing entities is 8, and extra entities is 11. So what I expect after using Radiant is the common entities should increase. The missing entities and added entities should decrease. And why should the common entities increase? Because whatever context I'm providing to the language model, I expect the language model to generate something which is reflecting what was provided to it and not delete or not add something extra. And this is after or during the process. So that this 10, think there is some reduction in the extra entities. And after the final epoch, we see some good results where the common entities has increased. So common entities, it went from 10, 10, 13. Missing entities, it reduced from 8, 8, 5. And extra entities, it went down from 11, 4, 3. So using this Radiant setup, we were able to generate an output which considers what was provided as an input context, and it reduces the redundant or unnecessary entities such as missing or extra entities. And speaking of the ECD, the divergence, ideal scenario, it obeys that and it reduces over the training epochs. So the best open source model we found was Llama 3.8 and the closed source was Qwen2. And the limitation here is, although we try to make sure that the factual consistency stays with using Radiant, there is a chance that given this alignment technique, there could be cases where there are adversarial attacks, which we haven't accounted for so far. And the last part is text to video. So again, this was something new I worked on since last time. So what is this? This is text to video hallucination. We want to address it and how. So we propose a benchmark called Vibe. It's a video benchmark. And following the same pattern, so far we have seen for language and images, we do it again, all over again, but for video, and the names are pretty self-explanatory. I'll just play one video in each category and we can go over the end. So here it says an airport runway with a large plane and cars parked on one side, but we don't see any cars. So this is an omission error. So even this is the prompt, there is nothing, there are no cars basically. Numeric variability, again, the name is pretty intuitive. It says 7 jars of full grain with rotten bananas. There are no 7 jars. Additionally, there are no bananas hanging over them either. Here it says 2 people on the surfboards, but there are more than 2. Then there is temporal dysmorphia, where there is some deformation, and then this person is flying his skateboard in the air along with time. So it started on the wall, but then somehow it gradually went into air. Then there is physical incongruity. There are lights coming off a passenger train, which is a bit odd. Then there is an animal more than the size of crowd of people walking over them. I think this is vanishing subject. So we see 4 people playing soccer, but then there is just 3 slices of orange are arranged on a plate, but then these slices somehow disappear in the plate. So the idea here is twofold again. We propose this large-scale vibe data set, and then we also provide some initial baselines by training the classifier. So we used MS Coco captions, and we did some random sampling as we selected these prompts, and then we used the state-of-the-art text-to-video models. We generated the videos, and then we again followed the annotation guidelines. We had some students to annotate the videos. We used these video embedding models to generate the video embeddings, and then finally we trained the classifier to predict the hallucination type. So these are the state-of-the-art, I think, 10 models, and these are the durations of the videos generated using each of these models, ranging between 1 and 2 seconds. On the left, the plot shows the duration, which we just saw, and the annotation time taken for each model's manual annotation. And finally, these are the results for the classification of the video embeddings in different hallucination categories. And we used transformer with different variations, say of GRU, LSTM transformer, blah, 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 and video MAE. And the best performance obtained both in accuracy and F1 score was with this combination of transformer and CNN. So we believe that this data set, along with this initial classification, will provide a benchmark as a baseline to the community, because again, this is first of its kind of work in this area. I think I just mentioned the implications. The limitations still are pretty similar to what we saw earlier. We just classify the videos in single hallucination category, and if there are multiple, we did not consider them. And it's limited to short video durations, but we intend to do for longer durations in the future. So the summary of my dissertation is, with the advent of Gen AI and the challenges, in particular hallucination, I developed several techniques, and I broadly put them under characterization, quantification, detection, avoidance, mitigation, and multimodal hallucinations, where I worked in both image to text and text to video domains. So since I've worked a lot in the past 2 or more than 2 years, there are some open challenges and future directions we think could be worth pursuing. So one is, we think that fine-tuning always helps, or probably not always in most of the cases, but that's probably not true. And there is one paper where it shows that if we introduce more knowledge, it learns slowly. And with fine-tuning, there is even a chance of hallucinating as against reducing hallucination. So that's something interesting. And then this is, we just saw in the ragability part, tug of war between knowledge, exploring and resolving knowledge conflicts. So basically the idea of this paper is, the model itself has its parametric memory, which we call internal memory. And the knowledge conflict arises when we try to augment this existing knowledge with some external sources. Now the language model has to decide what exactly to select. And this decision is not easy. So it says, I'm confused. What should I answer? So these are some open questions I think are worth digging into. Some future direction I personally am interested in is developing more advanced techniques for addressing multimodal hallucinations, because I think as part of my dissertation, I just barely scratched the surface, and I think there is scope for, say, using gradient, but in the multimodal area. So I think besides the publications which we saw, some other contributions of my work are some tutorials I delivered last year and even a few weeks back at LREC Calling and AAAI. I also had a chance to give invited talks at the MLOps annual conference and IEEE annual conference last year. We also got some media coverage in the Washington Post and Nature, where this, I think even created 2 slides. So it asks the question, is hallucination always bad? And the title or the opinion here says, honestly, I love when AI hallucinates. So there are some creative parts to it as well, not in the scope of my dissertation, but then that is something worth exploring. And then, can AI hallucinations be eliminated? Well, if we read the title here, it says AI hallucinations cannot be stopped because it's an inherent thing for the probabilistic language models to predict based on the probabilities. So they will stay. It's just that the extent to which they hallucinate will decrease over time, not anytime soon. So AI hallucinations cannot be stopped, but these techniques can limit their damage. And there are several groups working in this area trying to address this issue. And finally, to acknowledge, I would like to acknowledge dissertation committee, Dr. Amit Chet, Dr. Marco Altota, Dr. Amitava Das, Dr. Vignesh Narayan, and Dr. Ani Nankova. With that, I'll end my talk here, and I'm open to questions. Thank you.
Thank you, Mr. Rawte, for this very interesting presentation. It's 10:24, so you took a little more than an hour, I would say, given that we started a little late, which is good. I would like to suggest that we allow the audience who are not members of the committee to start with questions first.